Welcome to the inaugural Forum on Business Analytics in Florida. We're really delighted to have you here. We're so excited.
We're going to talk today about a topic that I've been doing for now over 12 years, which has to do with running controlled experiments. If you studied a little bit of statistics or even sociology, you learn about this idea of splitting your population into one or more groups. Let me see if that's going to work. Splitting your population into one or two groups, exposing them to some experience, and then running statistics to see if the treatment gets some measurable differences from the control. One of the things that sort of amazed me when I got into this field, I was at Amazon, and we were starting to run these controlled experiments. And I was shocked at how bad we were at predicting the good ideas or predicting the outcome of a controlled experiments. And I'll talk, this is a key theme that you'll see throughout this talk, which is it's very humbling because most of the time you come up with ideas, you do something, you build a program, you ship it out there, and you celebrate the exposure of the software to users. Microsoft used to have this idea of a ship it award. You shipped, you get an award. But it turns out that most of our ideas are bad. This is a key theme, very, very humbling, that I want to share with you through this. And the statistics about how right we are pretty amazing, and you'll get exposed to some of that. So I want to start with sort of one of the best ideas that happened at Microsoft, at Bing. A lot of the examples that I'll give are from Bing at Microsoft search engine. So somebody proposed an idea, and the idea was basically to change the way that ads were displayed. And it's one of many ideas. You know, it's very easy to come up with ideas. It's very hard to come up with good ideas. So this was one of those in the list. And it was out there. It was stack ranked. And it was delayed, I remember, in February, and in March, and in April, and in May, and in June. And we had all these features that were stack ranked above it. And by the way, I'm going back. I looked at the idea after it was declared great and looked back at how it was prioritized. So this is with hindsight that I'm telling you this. It was going to miss basically the rest of the year and will not get done that whole year. But it was trivial to implement. Right? So an engineer said, my God, this is such a simple idea. Why don't we just try it out there? And he went and implemented it over the weekend and started what we call the controlled experiment. And what happened is, the next day, an alert flyer says something is wrong with revenue. We're making too much money. And by the way, this is a really useful alert because people do have mistakes in the software. And somebody would register revenue twice by mistake, right? It would log this twice. And so the alert turned out to be really useful for us in many previous cases. But in this case, this was real. There was no bug. Our revenue increased by 12%. From the simple idea that took days to implement. Just to give you some perspective about this, we have several hundred engineers working on Bing ads, on the ability to display ads. And if they're doing a really good job for a whole month and they're running all these experiments, at the end of the month, if they can show 1.5% improvement to revenue, that's a great month. Right? So this person, or this idea that was implemented in a few days, was the equivalent of over 100 person-years of work. And we were just terrible at assessing the value. This is one of probably the best revenue-generating idea ever in the history of Bing, and we did not know how to stack rank it properly. So let me share with you what I'm going to talk about. This is a talk that has 4 parts. I'm going to give you some introduction, motivation, what are controlled experiments, why would you want to run them. I'll give you 3 examples. It's kind of a fun thing. I'll show you real examples of things that we ran and let you guess, see if you can guess which one is going to do better. Some lessons and pitfalls. And I'm going to talk about the cultural evolution, especially for an audience like this. It's important to realize that there's natural resistance to these types of changes. And in fact, Microsoft has gone through a dramatic shift in how we build software because of controlled experiment. We're still, haven't finished, but there's a lot of good signs that this is helping us a lot. So the first thing you have to realize is how software is being built. In the early days, classical software was built as sort of a classical sort of flow where you start off with somebody writing a specification. Programmers write and code the software. There's a big test phase, and then we release it. And you, in theory, get the ship it award. To give you an idea of how complex this got, at the point where I joined Microsoft around 2005, there was a ratio of 1-to-1 between developers and testers. It was so hard to test the software and to make sure it's compatible with older versions and that we implemented the spec. There was this whole theory of how to do this right, but it got to be really, really slow. So if you look at the key products at the time, like Office used to release every 3 years. The world evolved, and there's several books out there that I'm just mentioning about the idea that we can't go like this. We have to build an idea, we have to try and measure it and learn about the value of the idea, and then iterate. So the world goes into this continuous development cycle. And the idea is that you start off, and instead of trying to build the feature, you build what's called an MVP, or a minimum viable product. It's sort of the smallest nugget that you believe you can build that allows you to throw it out there in front of users and test it. And if it's a bad idea, you want to fail fast. And if it's a good idea, you may learn that it's a lot better than you thought, as the first example that I showed, and then you'll devote more resources to it and develop it more. And the way to evaluate things, the scientific way, and again, I'll get into the details, it is what is called a controlled experiment, or sometimes as it goes by the name of an A/B test. Right? There's an A and a B. And then the whole idea is to iterate through this. Is the more you can iterate, the faster you can iterate, the better you'll be able to develop software that customers love. And again, this is the theme. Why do this? Do this because we are very poor at assessing the values of ideas, because we cannot tell in advance if something is going to work or not. And the easiest way is to get it out there in front of real users, look at their reaction, look at their behavior against a new feature, and then assess how things are working. So we have lots of ideas. But not all ideas are good, and it's very, very humbling to see how bad we are. So how bad are we? Features are always built because somebody believes they're useful, right? Nobody wants to build something that they think is going to perform badly. So people come up with ideas, we stack rank them, we evaluate them. How good are we at assessing the values of ideas? So after having run a lot of experiments, this is sort of our rule of thumb. About 1/3 of their ideas are positive and move the metrics in the direction that we want in a statistically significant way, meaning a real movement, not due to chance. About 1/3 of ideas are flat, meaning you didn't hurt, you didn't do anything useful. It's a wash. And about 1/3 of the idea, and this is probably the most surprising part, are negative to key metrics. Right? So you're building something that you think is going to help users, and when you deploy it out there and you measure in a controlled experiment what happened, it turns out to be bad on the metrics that you define as the ones that you care about. And we're not the only ones doing this. There's observations from everywhere. I remember when I came to Microsoft, Microsoft was not running controlled experiments. I ran them at Amazon. I was director of data mining and personalization. And I told folks, hey, at Amazon, we used to fail more than 50% of the time. And people tell me, we have better program managers here. Right? So when you don't understand a domain, you always think we do it well. We know how to do this well. But it turns out at Microsoft, it's actually slightly worse than it was at Amazon. We used to fail about 50%. At Microsoft, we fail about 2/3 of the time in our ideas. And if you're running in an optimized domain, like Bing has sort of been running controlled experiments for a long time, there's fewer and fewer good ideas out there. We fail about 80% of the time on our ideas. So 80% of the time when somebody proposes an idea, it turns out to be flat or even negative. Very, very humbling. And you can see that companies that have used controlled experiments have observed very, very similar statistics. This is sort of now commonly understood in the industry that failure rates are very, very high. So how do you tell which ideas are good? Right? It's very, very hard. And the idea is to try and measure things. So what I want to share with you are a few ways in which people measure ideas before we get into controlled experiments. And some of these are flawed. So here's an example that happens a lot. I'll share it in the sort of context of Microsoft. Somebody comes to you and says, look, if we look at Office 365, 25% of our users that are new, they tend to leave. And we don't see them again. They churn after about 30 days. Right? And these are not real numbers. These are numbers for the presentation. But then they tell you, look, the people that use my feature that I built only churn at 10%. Therefore, my feature helps reduce churn. Okay? This is incorrect. Okay? There is absolutely nothing you can tell from these numbers about the impact of the feature on user churn. Okay? And the reason is that it is very likely that you're just latching on to some other factor that correlates with these two. So for example, in this case, heavy users. Let's see if I can actually point to things in here. Right? So if you have a heavy user, it is very likely that they will churn less, but it is also more likely that they would use some advanced feature, including the one that you built. Right? So given this data, you cannot say that your feature impacts churn. Okay? And I'm giving you some links. There's a PowerPoint that I wrote about some of the best causal claims. Right? This is a causal claim. My feature causes churn to reduce, all made from what are called observational studies. And these are heavily used in the industry. They're heavily used in medicine. And you can see some significant errors in the medical domain that people have made. Right? There's some famous examples of, for example, giving hormone replacement therapy to women. It was observed this is a very, very healthy thing. And then when they ran the controlled experiments, they realized the opposite conclusion actually happens. It tends to cause heart attacks in women. So let me just challenge you for a simple example. Go and look at your palm size. And I can tell you that this correlates with your life expectancy. So go and compare with your neighbor and see who's going to live longer. It's a true statement. The larger your palm, the less you will live. Very scary. Right? Who can tell me why? Age is a factor, but let's assume for adults. This is a true statement for adults. Bigger bodies, there's something a lot cooler than that. Okay, somebody called that out here. Yeah, don't try to bandage your hands. It is not a cause. Women have smaller palms and live 6 years old, 6 years longer. Right? So if you didn't realize this and all you did was plot, you're going to find this amazing relationship that tells you, hey, smaller hands causes people to live longer, but there's no causal relationship. It's just a correlation. We make this mistake over and over and over again in life, reading too much into correlations. So here's another example of a typical thing that people do in practice. Let's say you have a site on Amazon.com, and it sells Kindles. And you look at it, and these are your metrics for the first, for some period. And then at some point, you make a change. Right? You launch a new version of the site. It's the blue version. And lo and behold, a little later, come on, where's my cursor? A little later, major jump in sales. This is more satisfying than the previous one because you made a change and then something happens. The problem with this is that it doesn't take into account external factors. And in this case, Oprah said, hey, this is my new favorite thing. And in fact, if you were to run both sites concurrently, which is the basic idea of an A/B test, you will notice that the blue site always does worse than the green. They both jump up when there's an external event that happens, but oh boy, if you went from the green to blue, you would be making a mistake. Okay, so let me just back up and share with you what A/B testing is. And the concept is really simple. right? The name controlled experiment, by the way, refers to an A/B test or more complicated test. You can run A, B, C, D, E. You can get into multivariable tests and other things. But the concept is very, very simple. You have users that are coming in. You split them into two groups in an A/B test. One is the control, typically the existing website or software or whatever you're testing out, the layout of furniture in your furniture store. B is the treatment. You made some change, and you want to see how it performs. So you split the users randomly between these two, and then you measure everything you can about what's going on, right? The nice thing about software, we can measure a lot of things automatically. We don't have to survey. We just look at the user behavior. We look at performance. We look at clicks. We look at hovers. We look at everything we can about the user. And then at the end, we analyze. Right? So as I mentioned, there's, you can run ABN tests, which are multiple. You can run MVT, multivariable tests. It's got a lot of names to it. These are less important. Most of this talk, A/B test, is what I'm going to chat about. And then at the end, you're going to collect some statistics about what happened. And they're always going to be different. So if you're looking at revenue in A and revenue in B, there's no doubt they're going to be different. The question is this due to chance, or is it a real effect? And so you run statistical tests, very thing that you learn in Stats 101 called the t-test, that just measures if the change that happened could be due to chance, or is it likely because of the change that you've actually made, right? So if the t-test tells us that the change is statistically significant, then we say that B, the treatment, caused a change to those metrics. And this is commonly referred to as the scientific method. It's the way to prove causality. And why do this? So causality is the main reason that we like to do control experiments. The sort of the proof hand wavy goes like this. Everything that happens in the world externally to the system is happening to both A and B. Right? So that if there is a statistically significant change, it could either be due to the feature that I introduced, this change from the A to the B, or it could be random chance. Right? I might have gotten some better users in B rather than A. Because they're randomly split, the statistics allows us to see what is the probability of this happening, and therefore we can show. And this is why this is the gold standard. And for the way, in the US, for example, is the only way today to prove the efficacy of drugs. So if you look at the 1900s, the equivalent of the FDA then used to approve by panel of experts. And they realized that the experts are not as good as they thought. And so now we run clinical trials, or randomized clinical trials, which allow us to see reliably if one drug is better than the other. And then, I'll just say this is not the panacea for everything. There are certain things that you cannot run controlled experiments on. And there's some references about what you need, when does it apply. But it applies for a lot. There's also something that's very important to think about is this thing called the hierarchy of evidence. When you look at some claim that somebody's making, whether it's in a newspaper or in your own company, you should ask yourself, how reliable is that? How much should I trust this? So an observational study is an uncontrolled study. And you should be very skeptical when people show you the observational results from observational studies. And this is basically what the hierarchy says. At the bottom, there are things that are less reliable, physical observations or observational studies. If you get multiple observational studies, it gives you more credibility that something is going on. But above all these, if you're able to run a controlled experiment, that trumps everything below. And then if you're able to run multiple controlled experiments, then obviously this is becoming more and more reliable. OK, so just a few things about the scale. You read sometimes there was a control study comparing A to B. We run a lot of this. So every day, there's hundreds of experiments that are being run by our platform. And you can see the scale here. God, I can't point with this thing. You can see the scale here that shows you how Bing evolved from a few years where we ran a few experiments. And people realized, my God, this is making a big difference. We started to scale, run more. Today, we're at the point where sort of almost everything is tested. Any change that a programmer makes, unless it's a tiny bug, it runs through an experiment so that we can see if it's positive for the users. A lot of the times we find surprising things. You make a small change, you think this is innocuous, and then it turns out that it hurts something else you didn't think about. So big numbers. We're now running in multiple groups at Microsoft, from Office to Skype to Exchange. Experiments are usually done on at least 1 million users because we can. And the reason I'm saying this, we can, is that the more users you have, the smaller the differences that you can detect in the metrics. So if you're a startup and you only got 1,000 users, you can run a controlled experiment. You can only detect large differences, right? Maybe you can only detect a 5% improvement. For us, because we're so big, we want to be able to detect sub% improvements. And for that, you need a lot of users. And so we throw a lot of our users into experiments. In fact, almost all our users in experiments today. If you go and visit Bing today, you're probably in 15 experiments. We tend to use 90% of our traffic for experimentation. And we keep a 10% sample on the side to actually check the experimentation system itself, that the system itself is not hurting. But what that means, though, is that there is no single version of the software anymore. Right? If you're exposed to 15 experiments, and they're all what are called orthogonal, they're operating independently, there's like 30 billion possible variants that you fall into. Okay, that makes testing and debugging a whole new meaning. So now when somebody reports an issue, we have to say which experiments were they in so we can try and replicate that. So that changes a lot of how we build software. As the graph shows, until about 2014, our own system was the limiting factor. We couldn't run enough experiments. Today, everything is being tested through the system. So what I want to do now is sort of the fun part of the talk. I'm going to show you, it's actually 3 experiments that Microsoft ran. Each provides some interesting lessons that I'll share with you. They all had enough users, so you don't have to worry about, you have enough users in them. They're all statistically valid. And for each experiment, I'll give you something called the OEC, the Overall Evaluation Criterion. This is the metric that we care about. Right? And this is something very, very important. Before you start an experiment, you have to say, what am I optimizing for? What is that metric? And it's a game. Please, after lunch especially, I'll wake you up. I'll ask you all to stand up. Come on, guys. Make an effort. Stand up. Make sure to wake you up. Good exercise. There's enough people in the room. The statistics are probably going to work out, and I'll tell you what's going to happen. I'll give you the 3 examples. We'll each have 3 choices. I'll show you an A and a B, and I'll ask you if A wins, and the difference is statistically significant, meaning we know that there is an effect there, or A and B are approximately the same, so we couldn't detect a statistically significant difference, or B wins, right? And you're going to guess, and if you get it right, you'll remain standing. If you get it wrong, you'll sit down, and we'll see how many people stand at the end. And I'll just tell you that there's 3 choices. Actually, I have to fix the slides because I removed one question because the talk time is limited. So there's going to be 3 choices. So it's going to be 3 to the third, which is 27. And we'll see how many people stand up at the end of the day. Given this room, there's probably going to be, if you guessed completely randomly, right, just flipped coins, there should be about something like 10 people standing at the end of the third question. So let's see how many you can get right. So the first example is on the MSN homepage. Remember the OEC, the metric that we care about? Are clicks. We want to know if people click on this thing or on this thing in B, or on any of these suggested queries at the bottom. Right? So people have to click either on the search icon or on the search box or on these popular searches. So let me highlight a few differences from you that you understand what we were testing. First of all, both boxes, the outside box is the same size. Very, very important. If one of the boxes was bigger, then it might affect things below it. They might fall below the screen, below the fold. So the boxes overall are the same sizes. But you'll notice that the top one is a little bigger. Right? It's got more, the inside of it, the white space is a little bigger. So we made that larger. The icon is a magnifying glass, whereas in the other version it's called search. And then the word popular searches only appear at the top version. Right? OK, so now think about which one is going to be better for click-through. Raise your left hand if you think A wins. Raise your right hand if you think B wins. But don't raise your hand if you think they're about the same, meaning no statistically significant difference. So I'll give you a few seconds to think about it. And notice, by the way, that some people are raising their right hand, some people are raising their left hand. This is very, very typical, right? There's a debate. Which one's going to win? Fewer people are not raising their hands, so you're very comfortable, confident about your choices, which is also a very, very common mistake. If you raised any of your hand, please sit down. Well, this is a lot worse than random. OK, so the point here is stop debating. Get the data, right? Notice that if you were in a room and some people raise their right hand, some people raise their left hand, you'd be screaming at each other which one is better. It turns out it doesn't matter. Both are doing about the same. So remember, I told you about a third of the experiments do not move our OEC. OK, second example. And by the way, those of you that are sitting, feel free to enjoy this as you watch some of the famous people in the room vote. OK, so the question, this is a little more complicated. So the idea was, should Bing add what are called site links to ads? If you look at the right example, the bottom row has what are called site links. These are links to the destination that improve the predictability for the user about where they'll end up. So if they see an ad for insurance, they can tell from the bottom, or they can click on one of those bottom 4 links to get them to the right place, right? Do they want to get a quote? Do they want to read about the company and things like that? So the question was whether we add this row to the bottom. Now, I'll tell you something that's sort of a rule of thumb, which is if you make something bigger, it will get more clicks. Right? So if all I did was to ask you which one gets more clicks, A or B, you should all vote B because it's bigger. It's a very strong rule of thumb. We've learned it over and over again. You take more real estate, you will get more clicks. But there's a problem with that. We know, we've shown, that if we take up too much real estate for ads, people hate it. Right? People want to see the algorithmic results. The algorithmic results are the ones that we determine have high relevance. The ads are the ones that we get money from. So we've proven over and over again that if we take up too much real estate, we will hurt the user experience. They will leave more. They will, over time, decline in usage. And so we've established ourselves sort of a constraint, which says this is the amount of space that we're going to give ads. And this is why this problem is so interesting, because now I'm not going to just ask you which one's better, A or B, but I'll ask you which one is better given the constraint that they have to occupy the same amount of space on average. And what does average mean? It means that I can show 3 ads of B or 4 ads of A, right? Because there's about the quarter of a difference between them. And it doesn't have to be on the same query. I can display for this query 3 ads, and the other one will show 0, or et cetera. I can determine how to optimize. But on average, I have to take up the same average real estate. OK, so let's summarize what's written here. The pro of adding these site links, you get richer ads. The users are better informed where they're going to land. The con is that you can only display 4 A's versus 3s of B's on average. And we also know from just measuring the performance that variant B is slightly slower, 5 milliseconds. Millisecond is 1/1000th of a second, because it takes us a little more time to compute these, and because the page that we send has a larger payload. So raise your left hand if you think A wins. Raise your right hand if you think B wins. And don't raise your hand if you think they're doing about the same. OK, so I see the people voting. He's got his right hand. He's got his left hand. If you raise your left hand, then you were wrong. Please sit down. If you did not raise your hand, you were wrong. Please sit down. Tens of millions of dollars annually. So this change was worth tens of millions of dollars, and we could not tell if it was going to work or not. There's a lot of debate, just like in this room, about whether this is a good idea or not. We tested it. We learned that this is worth tens of millions of dollars. As I said, this is a great example. There's others where we changed revenue by $100 million. And the surprising thing is how little effort you have to expand in order to implement some of these ideas. Conversely, we had massive strategic efforts at Bing. A few years ago, you may remember we did this thing called social integration. We would expose results from Twitter, expose results from Facebook. We built real-time pipelines. It was, complicated things. 100, 200-person years went into that effort. 0 value. Nothing that we could see is actually valuable to users because of those integrations. OK, let me do the last example. It's called SERP truncation. Search is an acronym for Search Engine Results Page. You're probably familiar with it. You type a query into your favorite search engine, Google, Bing, Yahoo, whatever. You get results. And they have the results going from the top to the bottom. And normally, the rule of thumb, which was established years ago, was show 10 results. OK? What are we going to do here? We're going to measure the click-through rate on the first page that comes up when you issue a query. There are complications if people click and go back. I don't want to get into those complications. I'll make it easy for you. People type a query, you look at the first page that comes up. What is the click-through rate? Meaning, did they click divided by the number of impressions that happened? In version A, we show 10 results. In version B, we just remove the bottom 2, so there's only 8 results. Everything else remains the same. The ads are the same. If there's a task pane on the right, it remains the same. The related searches, if it shows up, is remaining the same. The other difference is version B is slightly faster because there are fewer results, so we have to send less things over the wire. And the computation on the server happens to be about the same, so we don't save time there. So just a little bit faster. So the question is, which is better? Should we show 10 results or 8 results? Raise your left hand if you think A wins with 10 results. Raise your right hand if you think B wins with 8 results. Don't raise your hand if you think they're doing about the same. OK, there's 3 people here. One is right hand. The other 2 are left hand. Oh, my God. Sit down. OK, so there's a paper that we wrote where we sort of this rule of thumb. It is very, very hard to change the click-through rate on the page. We tried so many examples where we move things around, where we cut results and add results. And all we do is we tend to cannibalize other areas of the page, and traffic just moves from one place to the other. There are obvious exceptions. I'm not going to say that there aren't. One of our key goals is to improve the click-through rate, and we have some versions of that that are successful. But by default, it is very surprising how much just traffic moves from one area to the other when you change your results. Okay? And then in the paper, we share a lot of surprising examples. We actually went down, just to give you an idea, we truncated the page all the way down to 4 results. 10, 8, 7, 6, 5, 4. The problem when you show few results is people report that the page is broken because they see it white. And so we only did that when there was enough, sort of the first result was sort of biggie with D cards, and then we could use it. But if you look at Bing today, we did something tricky, which is we display 8 results. But if you click and go back, we actually say, oh, something didn't work. We'll give you more results. So we actually go from 8 to then showing you 12 or 13 or 14. OK, we're done with the first 2 parts. What I want to share with you is some lessons and pitfalls, and then talk about the cultural evolution. So the first one, very, very important. You got to agree what you're optimizing for. The most fundamental mistake that I've seen people do is they don't know what they're optimizing for. OK, so I'll give you one example. Microsoft support. Relatively large site, gets a lot of traffic. People go to support.microsoft.com, or they click from the home page for Microsoft.com. And they came to me and said, we want to run A/B tests. Cool, you want to run A/B tests. So I'm sitting there with all these important people from the Microsoft support side, the executives, the technical people, and I say, do you know what you're optimizing for? And they said, Ronnie, we read your papers. We know you have to do an OEC. We all agreed time on site. I said, time on site? You're a support site. Is more time better, or is more time worse? Now the room split into 2. Half the people thought more is better, and half thought more is worse. Right? Because the logic was, well, if they spend time on our site, they're not going to Google or other places. The other version is, if you're less time on the site, we managed to solve your problem. Okay? Terrible metric. Time on site for a support site is a terrible metric. For other sites, if you're building a portal like MSN or Yahoo, then time on site makes sense. You want to engage the users. You want them to play with you. You want to stay with you. But for a support site, really, really bad metric. What you should try to measure is success. Are they able to solve their problem? That's not always easy. I'll share with you a couple of more examples. One is from Bing. So Bing, as a strategic goal, optimizer for what is called query share. We look at the overall market. There's a company called Comscore. It reports the number of queries executed in the US by all search engines. And we look at our share. When Bing launched, it was 9%. Today, we're 21%. We made some nice progress over time. So we measure ourselves on query share, and we measure ourselves on long-term revenue growth. Now, the problem is you can do short-term things to move these metrics. For example, you show more ads. If you show more ads, you're going to increase revenue immediately. There's no doubt about it. But users will abandon more, and we've shown this through controlled experiments. We show too many ads, people don't like it, and they leave, because the relevance of ads is typically lower than the relevance of what are called algorithmic results. And revenue turns out to be this constraint optimization problem. Given some budget for number of pixels on the page, or vertical pixels, can you optimize revenue through that? Now, the other one is queries per user. Right? How many queries you visit Bing, how many queries do you do? If you do more queries, then we get a larger share of query share in the US. So that seems like a good metric. Turns out to be a really, really bad metric. We know that when we degrade the results, when we show you worse results, people issue more queries. And the reason is they're not finding their results. So they'll refine the query, they'll add a word, they'll do things. And it turns out, really, really bad idea. So we came up with another metric. And again, if you want to look at the details, there's a sort of an explanation of this. But sessions per user is a much, much better metric. If you come, you have a session, you have a task to do, we want you to issue as few queries as you can to get the result. But if you come again and again, that indicates that we're doing a good job. So at Bing, we have this OEC, sessions per user is one of the key metrics. We have several others. We combine them in order to form our OEC, which is a fairly complicated metric. And every year, as we learn more, we actually make small modifications to it. A few examples of some bad OECs, just to highlight one that I saw a few months ago. Some guy comes to you and says, hey, 2% of our queries end up with no results. And so the typical manager will say, we got to reduce that metric. Let's prioritize the team and make sure that we lower the no results metric. It is very, very easy to fool yourself. Here's an example on Amazon where I go and type brochure paper. There's no results. What do? They remove one of the keywords in my query and show me this. Crap. So they move the metric. Is it a good way to move the metric? No, it's a terrible way, because you're showing people terrible results. And sometimes it is better to show no results. And so think a lot about your OEC. Very, very challenging, very hard to get right. Second thing is, and forgive me if I go a little bit technical for some of the people here, when you run an experiment, you will get something called a p-value. When you see papers in literature, in sociology, or medicine, or other things, the most important number in the paper is the p-value. The p-value tells you if your result was statistically significant. There's a rule of thumb that says if you're less than 0.05, statistically significant. If you're above that, then you can't tell if there's a difference. Usually, the assumption is no, there isn't. And so it's very, very standard. Everybody's using that. It is also very, very commonly misinterpreted. So if you heard of a p-value, here are some things that are wrong about the p-value. If p equals 0.05, then the null hypothesis, the null means there is no difference, has only a 5% chance of being true. That is not correct. If you get a non-significant difference, meaning the p-value is greater than 0.05, then there is no difference between the two groups. Again, that is incorrect. Your experiment may be what is called underpowered. You may not have enough users to detect the change. There is a change, you just cannot detect it. What you want to do in these cases is say, I can detect a change of this magnitude. Remember, I mentioned to you, Bing runs experiments on a lot of users because we can, because we want that delta to be small. The more users, the more power I have to detect small differences. And then these other two are also true. And the point is, the p-value, as it is made, gives us a probability that assumes there is no difference. And then we see the value, and we say, what is the probability that the value that we saw is greater or equal, sorry, that the real value is greater or equal than the value that we saw, assuming that there is no difference, or assuming the null hypothesis. What we really want is the opposite. We want the probability that the hypothesis is true or false, given the value that we saw. For that, you have to do something called Bayes' rule. You have to look at historical data. I'm not going into details. I just want to share with you that it is often misinterpreted. If you want to make sure you understand it better, you may want to do a little bit of reading on what p-values are. The third point is validating the experimentation system. It's just amazing how easy it is to get the results wrong. And I've seen people produce values that have 6, 7 digits after the decimal point, and the first one is incorrect. So you have to build a system that you trust. We have the statement, getting numbers is easy. Getting a number you can trust is really hard. It's kind of interesting here. 2 really good books on Amazon. Really fun books to read. I encourage you to read them if you want to learn more about A/B testing. But when you talk about the math, they both get the math wrong. Okay, some things that we do, we run something called AA tests. Remember I told you normally do an AB? Here we're going to use the system and run A against A. Now what do you want a system to say? You want a system to say there is no difference 95% of the time. Well, it turns out when you first start to use AA tests, you will realize that something is wrong with your system. We found a lot of bugs this way. Another thing that we do is, again, as a technical, interesting test. If you were running an experiment at 10%, 10%, what you want to make sure is that you get approximately the same number of users in A and B. Now, let's say you run an experiment, you get these numbers. I'm showing you some large number there. 821,000 versus 815,000 and change. And it's not exactly 50. It's 50.2. Is that OK? Turns out it's not. When you deal with large numbers, the A and the B have to get very, very close in terms of the number of users that you get, or else there's a bug in your system. And in this example, the probability that this split could happen by chance is less than 1 in 500,000. So unless you run 500,000 experiments, this should not be happening, or should be very, very rare. We do this test, just to let you know as an example, we run hundreds of tests a week. Every week this thing fires. Tells us, hey, that experiment, there's something wrong with it. That gives us a lot of intuition. I'm not going to go into this slide. It's a little bit technical. But here's a good example of an experiment that we ran that yielded this SRM, the sample ratio mismatch. So we had this, MSN has this main screen called InfoPane. And you could scroll through the slides, or it would rotate with time. And the left version has 12 slides, and the right version has 16 slides. So somebody said, we're going to invest more money. We're going to have more editors put these up. Is it worth it? It's a fair hypothesis to test. And we ran this experiment. It turned out that A was much better, which is sort of non-intuitive because we think if we spend more money building more information, it should win. But A was a lot better. But the problem was there was a sample ratio mismatch. Right? We didn't get the 50-50 that we wanted, or very close to it. There was a slight difference in the percentages that we expect. Can anybody think of why this would happen? It's a tough one. I mean, it's one of those things that you don't think about. But it turns out that user engaged so much more with the treatment that the system for classifying humans versus bots classified more of them as bots and took them out. Right? Bots are these robots that crawl the websites. They're automated. They're not human. And things improved so much that they got classified into bots, thrown out, and therefore it looked that they were doing worse. So after fixing this, the treatment turned out to be a lot better. And then there's issues with data quality. Outliers present a significant challenge. I'm giving you an example here from Amazon. It turned out that if you're looking for some changes, it's possible that a single large entity buys enough to skew a small A/B test. There's another example of why we want to run larger A/B tests. And it turns out we dug into this at Amazon. It turns out these were basically libraries that were buying a lot of books for large amounts of money. And so we had to deal with it by doing something to truncate the metric or to make it more robust. So this is what we do today. We do capping. Bots at Bing are a really big issue. Just to give you an idea of how bad things are, 50% of our traffic, just over 50%, is coming from non-humans. This is scary, right? Like more than half of our traffic is generated by automated bots instead of humans. And so we spend a lot of time trying to identify them for multiple reasons, other than for experiments that we want to remove them, but they're costing us a lot of money. And if you know that something is a bot, you can change your performance, for example, and give her slower response time. It doesn't matter to them much. Us being able to slow down the response allows us to save on hardware. So it's a very important issue for us. And this is just a funny thing, but I was driving in Seattle one day, and I saw this guy who's obviously making a lot of money from writing bots. That's his license plate. OK, so one thing to remember, the best data scientists are skeptics. We have this law, which is called Twyman's Law. Guy Twyman used to measure audience in the UK, and he had this statement: any figure that looks interesting or different is usually wrong. Okay, and we use this a lot. When somebody comes to you with a real success story, I moved something by a lot. If it's too abnormal, we question that. We go drill in, and 90% of the time we found some bug. And there's the first example I showed. Sometimes it's real, but those are very, very rare. So let me talk about the culture. We started to use controlled experiments, and we proposed it. A lot of opposition. Right? It's difficult to get somebody to do something when the salary depends upon not doing this. People believe it hurts them as decision makers. If you have a program manager that is used to defining the next version of Office and then executing it and celebrating when you ship, and now they have to change into a world where they propose all these ideas for the next version, 2/3 of the ideas are bad, and we tell them to iterate, they don't feel as good, right? They're standing in the organization, it's like, boy, your ideas are pretty lousy. You fail more than half the time. So it's a cultural challenge to be able to admit that we're not that good. Very, very challenging. I mentioned this thing. We have editors who are designed and get paid to select the designs or the headlines for the articles that appear on MSN. It turns out we do much better than them if we automate them. Right? If we just tell them, give us headlines, we'll automate them. But they feel that it's their job to select the headlines, and it's hard to make those changes. They may hurt their professional standing. Like I've heard people say, we know what we do, don't bother us, it's in our DNA. I've had this guy, as a senior VP, say, why don't we just do the right thing? As if you know. There's sort of a model that we think of as the cultural progression towards becoming data-driven. Hope you'll enjoy it. It's kind of fun, a lot of historical stuff. The first stage is hubris. Everybody thinks that they know what to do, and they're very sure of it. So here's a true story from 1849. John Snow claimed that cholera was caused by water. Everybody thought at the time it was caused by miasmas or air. Okay, so this one landlord has a building, and the tenants complain that the water stinks, and cholera is frequent. And they say, hey, this could be the cause. But remember, he doesn't want to believe that, right? He's sure that there is no problem because it's, the belief is this comes from air. So, he goes and comes to the tenants and says, look, there is no problem here. Takes a bottle, takes water from the tap in the building, and then he dies 3 days later. Okay, so hubris is a problem, could cause death. Real story, by the way, pretty amazing. If you're sure of ideas, just test them, evaluate the assumption. The second stage is measurement and control. This is just an amazing story about somebody called Semmelweis. He worked at the Vienna General Hospital. It was a teaching hospital. And at the time, there was a disease that we don't have today called childbed fever. It killed more than a million women in that century. And it had no explanation. So he starts to collect statistics for the first time. He says, let me look at the different wards in the hospital. And he finds this amazing result. 15% of women in his ward that are staffed by the doctors and the students die. By the way, just think of the statistics. It's like, you're a woman, you come to the hospital, and there's a chance of 1 in 6 that you will die. But he looks at this other ward, which is attended by midwives, and they have a 2% mortality rate. Interesting. Now, when that happens, you don't know. Maybe they get the easy cases, he gets the hard ones, right? You have to try to control the differences. So he tries to control for everything that is different about what happens to his ward and what happens in the midwife's ward. So he looks at birthing positions, he looks at ventilation. He comes up with all these ideas about diets. He even gets down to laundry. Is it possible that the laundry is the cause? I mean, you can see how far he goes. There is nothing that he finds that differentiates between the treatment that the women get in his ward and the midwife's ward, yet there is a huge difference in mortality rate. He goes away on sabbatical. This is one of those things that professors get to do. And he comes back, and the students are elated. Hey, look at this. Our death rate is down significantly. So he's like, oh my God, scratching his head. Is this related to me? And it turns out it is. At the time, they were doing, every morning they were teaching and doing autopsies on the cadavers of the women who died the day before. And so he comes up with this idea, the fact that we're looking at the bodies, the fact that we're looking inside, we must be bringing particles from the dead people to the live women, and that's what's killing them. Okay? So today we know that there's this thing called germs, but at the time, this wasn't clear. And so he comes up with an experiment. He says, tries a set of cleaning solutions, cleansing agents, and he observes that when he used chlorine and lime, the death rate goes down from 18% of the time to 1%. Right? So just simple experiments with a conjecture lead him to drop the rate from 18% to 1%. Huge win, right? Wrong. Nobody believes him. Where are these particles? How is it possible? He gets dropped from his post at the hospital. He goes to Hungary. The new hospital does the same thing. He shows them in Hungary that he can drop the death rate below 1%. The students try to publish a paper about the success, and the editor writes back, look, stop believing in this hogwash. And then he suffers a mental breakdown. He actually believes that the fact that he's not able to convince the world of this is killing a lot of women. He's right. And then this is now called the Semmelweis reflex. Right? This is sort of a rejection, a reflex-like rejection of knowledge, because we believe it can't be the case. Right? And this happens in your orgs. Somebody's so sure about something, they're not willing to listen to the data. They always poke holes, and they find reasons why this is not reliable. And so there's a name for that. Now, is this only true back then? Obviously this can't be true today, right? Of course it is. So in 2005, there was a study that published that doctors and patients that don't wash their hands contribute to 2 million healthcare infections and 90,000 deaths annually. So we have the data, yet people don't wash their hands. Okay, the last stage, if you get to it, if you're lucky enough to get to it, is what's called fundamental understanding. Louis Pasteur showed that there are germs, strep germs, that are in the blood of women that have childbed fever. And in 2008, 143 years after Semmelweis died, there's now a 50-euro coin to commemorate his success. Okay, so this is the evolution. I think in many areas today, we are back in the 1800s in terms of our understanding. If you look at sort of designs for mobile, we still grapple with, how should we make designs for mobile systems and things like that. For your phones, it's just small real estate. And we don't understand that we're still in sort of the alchemy days, or the days of the earliest days where we don't understand this. Let me end up with a hippo. This is something that most of you have on your desks, and you probably didn't understand why. This is the reason. HIPPO stands for the highest paid person's opinion. It's an acronym that we came up with. The guy Avinash from Intuit and I were meeting, and he mentioned a variant of this called hypo, and I said that can't work. At Microsoft, hypo is a high potential person. And then I modified it to hippo, and we made this little hippo that you see out there, and we gave thousands of them at Microsoft. But it's a really, really important point. If you can get from a hippo making the decision, or listening to the highest paid person's opinion, versus empowering them with data, you will make a fundamental difference to your business. This is an interesting fact. Hippos kill more humans than any other non-human mammal, mostly in Africa, but it is a true fact. People walk at night, they tend to step on them, and they're not very friendly to people who walk on them at night. Listen to the customers. Don't let hippos kill your good ideas. There's books, and we've actually seen this too. We cannot find a good correlation between your level and the org and the value of your ideas. Like, we throw the ideas into experiments. They tell us that some work, some don't. But there's not a lot of correlation between the ideas. There are some people that are really good at coming up with ideas that work. They are not necessarily the execs and the managers. Okay, so we put this over your desk. So I want to just summarize some things. make sure to understand what you're optimizing for. This idea of an OEC, an overall evaluation criteria, is just hard to assess the values of your ideas. Listen to your customers, get the data from the actual customers, and then prepare to be humbled. This is, if there's the 3 examples that I showed you where nobody was standing up at the end, is that more humbling? Right? Statistically, if you guessed randomly, there would have been 10 people standing. So worse than random here. Make sure to get your statistics, compute them carefully. Getting numbers is easy, and getting numbers you can trust is much, much harder. We've learned this over and over again. We keep validating our system. We find bugs. We try to do more complicated tests. And then experiment often. I mean, this is one of those things where I showed you the graph of scale. If you can triple your experiment rate and remain with about the same success rate, whether it's 30% or 20%, you can have more successes. And it's only those that really count if you're data-driven and you launch, you ship to users, only the things that are really useful. So try to accelerate your innovation by lowering the cost. This is another thing that we worked a lot on. People say, oh, I have to run an experiment. It gives me more work. We've built a platform that makes it easy to run experiments. There's no excuse not to run them. It's hard to get to that state. I'm not saying it's easy, but it is possible to do that. And then the URL is on the HIPAA if you want to read a little more papers. Some of them are more technical. There's a link to the talk. And then sometimes I tweet at Ronnie K. Thank you very much.
Time for a couple of quick questions from the audience for Ronnie.
Yes.
The 2016 elections was the heaviest, the most analyzed elections in history. What went wrong?
What went wrong? Yeah, I'll repeat the question. So,
2016 election was the most heaviest analyzed election in history. What went wrong?
so I'm not going to do justice to the many articles that were written about what went wrong, but it was not a controlled experiment. Look, predictive modeling is hard, and there's no doubt that at the ratios that we're looking, it was, at some point it was close, and people starting to call it out. We have a complicated system of voting, which is not majority. So many things are working against sort of the standard mathematical analyses that you can do. And when you look back, yeah, it was a serious mistake by a lot of people who were well respected. And these things are going to happen. So we are humbled over and over again where our models get it wrong. The thing to remember, and this is always something that I'd like to highlight, you can come up with a system which is 70, 80% accurate. The question isn't whether you can get to 100. The question is whether you're doing better than the human that is trying to predict with smaller amounts of data based on intuition. I think over and over again we've shown that the machine learning systems that we have are more accurate than the humans that are sitting down and look there in the eye and decided to give you the loan or not. Right? The automated models do perform better. They're never going to be 100%. We will always see things like the election here. We have an error rate. It's higher than we want. But if your model gets 80% right, it's a massive success. Relative to humans, it tends to get 65% right. That's the thing that really matters. The story with the bear, right? 2 guys are hiking in the forest. They see a bear. One of them starts to take out the hiking boots, puts sneakers on. Second guy says, "You can't run out a bear. I don't have to outrun the bear. I have to outrun you." Right? And that's the story. You have to be better than the alternatives. Yes.
So you use Bing as an example. It's great because you have access to that population. What about a product like Cortana? We're using it locally, but how do you run tests?
Okay, so the question is, let me repeat. We can run experiments on Bing because we have access to all the data. What about other products? You mentioned Cortana, which is a surprising one because that's powered by Bing. But let's say you're looking at Office, right? The answer is we are now moving into a world where everything is instrumented. So we know a lot about what you guys are doing anonymously. We log a lot of the metrics. You have an option when you install software to say you're willing to help by providing information. We log those things. About 35% of users actually allow us to look at their data, and that ends up being millions of users. And we make the decisions just like we do for Bing. So the world is moving. If you use any product today at large scale, they typically collect enough data to help make those decisions. This is changing the world of software. It's only possible in the online world that we have today. It was not possible 20 years ago when you ran a client that was never connected. But if you're connected, there's a lot of logging going on. There's some problems with that, with privacy that we have to grapple with. But it is, ultimately, it's good for users. Like, I strongly believe that, you know, the fact that we are able to log allows us to build the features that you guys, at the end of the day, need. We'll build better products for you. Yes?
Probably one last.
How do you decide which ideas are worth testing, or which hypotheses?
Yeah, so how do you decide which ideas are worth testing? So the biggest cost to testing an idea is the implementation. Somebody has to build the feature, right? And the corollary to that, which is very important, which is sort of the first example, if something is cheap to test, don't bother trying to assess it. Just go ahead, build it, and get it out there as an experiment, right? Now, if something is complicated, then there has to be a prioritization process like there used to be before, where we do some assessment of the value. And, you know, we're not great at this. You know, I have to admit, it's very, very humbling, as the first example shows. But what we've learned, one of the things that we learned, is try to implement the minimum viable product. Build the smallest thing you can that allows you to get the data about the value of the idea. Right? And that may be smallest in terms of a smaller feature. That may be in terms of a feature that only works on certain browsers. This is a very typical thing that we do. To support all browsers, very hard. To write it just for Edge or Internet Explorer, a lot easier. I only have to test it on one platform. So we build it. If it doesn't work there, we have learned our feedback. We can decide if to fail fast.
Join me in giving another round of applause to Ronnie.
Thank you very much.